Welcome to the first tutorial of the day on Web Cryptography Workshop. I'm going to be doing the presentation. I'm Charles Engelke. I'm CTO of a company called Infotech that has been using cryptography for sealed bidding and other applications in the transportation arena since the 1990s. And we have recently started moving our applications to the web now that we have the Web Cryptography API available. So that's what we're going to be talking about today. Lori?
I'm Lori White. Until last year, I was a professor at Mercer University in computer science. I'm here as the teaching assistant, and somebody who's gone through these labs a lot of times and who's done a lot of labs in my career. I retired from Mercer last year. I started at Google last month. My manager wants me to tell you that I don't know anything. And if you know about Google, it takes more than a month to figure out what's going on. I will be in developer relations in the cloud platform. And unfortunately, about half of the stuff I've heard about won't be public until the end of the month at the GCP Next conference. So look out for that, but please don't ask me about cloud, but I will be more than glad to talk to you about Web Cryptography. And as an instructor, I know the important things are go out the door to the right, just past the escalators, and to your left will be the restrooms, and we have a break at 10:30, and you know about it. So let me move back to my position.
Okay, and Lori is going to be moving around, and anytime you get stuck on anything, just try and get her attention, and she'll come and give you a hand.
And if anyone's missing the files, we do have some USB keys with us.
Yes. In fact, let's talk about that, the workshop materials. There's a GitHub repository at github.com/engelke/fluent2016. We should have closed that and updated it. We tweaked it a little bit last night, although the earlier versions were still okay to use. Or we have some USB keys we have here that we can loan so you can copy it onto your machine that way. If so, just get Lori's attention and she'll bring the USB key over to you. The second resource you're really going to want is the Web Cryptography API specification, which is a hard document to read. The specification is really written for browser vendors to tell them how to implement this. It's not written for developers to tell them how to use it, but it's the only resource that really defines the entire API that's available today. So that's available on the web, and you can just use Google if you don't want to write down this URL. Some of the key things that are in that specification that are scattered through this large document, I've copied over into a little cheat sheet. So let me bring that up. There we go. The first page lists all of the methods that are in the API along with the parameters they take. The second page tells what kind of algorithms can be done for encryption, signing, digest, and so forth, and some examples of algorithm identifiers. All this stuff is in the actual standard spec, but it can be pretty hard to find. We were going to hand this out on paper, but we didn't get it done before we got here, and we haven't had access to a printer since. So it is on the slide, on the repository folder you've got. All right, so that's the background. What are we going to do today? We're going to talk first about some background, what this API is and why it's important, why you would care, what you might want to do with it. We're going to give a little bit of core concepts because we're not sure that everybody's got the exact same background in cryptography and JavaScript that we're going to use. Now, you don't need a lot of background. We'll cover what you need if you don't already have it. But you do need to be familiar with the concepts of what encryption and decryption are and basic JavaScript and callbacks. Then we're going to spend most of the workshop hands-on with the API. We're going to introduce a lab, we're going to talk about it, then we're going to give you guys some time to work on it, and then we're going to go over the solution together. Now don't worry if you don't finish all the labs or even any of the labs. The value will be really trying to work your way through them, but we may not have time to let everybody finish everything. All right, as I mentioned, the API is a W3C candidate recommendation at this point. The way that the W3C standards work is they go through different stages. The stage we're at right now is candidate recommendation. We've been there since December of 2014. The next stage is to become a proposed recommendation, and then after a couple of years, it will become just plain recommendation. We had hoped that we would be going to a proposed recommendation by now. By the way, I joined the working group that is responsible for this spec last year. However, you cannot become a proposed recommendation unless everything in the recommendation is independently implemented by at least 2 different browsers. And there are some things here that still aren't quite there. So we have a choice of either taking some stuff out of this spec, or if we think the browser vendors will be coming out with it soon, waiting a little bit longer. We're kind of straddling the fence now. We're going to wait a little while before we give up and take some things out of the spec in order to go to proposed recommendation. Despite that, it's very stable, and it's really been stable since the second half of 2014, even before it became a candidate recommendation. It's in lots of browsers, and what it does is provide access to native crypto libraries from within the browser using JavaScript. Which raises the question, why do we even need this? Why don't we just write our cryptographic algorithms in JavaScript and use them? JavaScript is certainly capable of doing that. Well, there are 2 problems. One is just the fact that these algorithms are complex and slow, and JavaScript itself is relatively slow. But a bigger problem is that it's very hard to write secure cryptographic libraries. In order to be secure, it's not enough that you actually produce the right outputs given the right inputs. You have to be careful not to inadvertently leak any information about the operations you're performing, by perhaps taking longer to do some operations than others. These native crypto libraries that the Crypto API uses have been battle tested. They're all at least 15 years old. They've all had vulnerabilities discovered and fixed over the years, so we didn't want to start fresh and have a lot of new vulnerabilities in JavaScript. We want to use these native crypto APIs. These are also the same libraries that your browser uses when it establishes a secure connection to a secure website. So the same thing is being used by your code within the browser. The API is available on pretty much all current standard web browsers. The latest versions of Chrome, Firefox, Opera, and Microsoft Edge, not Internet Explorer, Edge. Now, Apple Safari still has a prefixed incomplete implementation. And although there are a lot of pieces of it there, I don't have any examples because I wasn't able to find enough pieces that could string together to be a useful business case yet. Apple doesn't really announce their intentions, so we don't know when they're going to get around to fully supporting the API. They've been in the news a lot recently talking about cryptography. My hope is that that makes them think that, hey, maybe they should get that fully finished in their web browser as well. Some of you, such as my company, are going to have to support users using Internet Explorer. And if they're using Internet Explorer 11, the good news is that there's an old version of the API that is nevertheless pretty complete and usable in Internet Explorer 11. We're going to spend a few minutes talking about it, but not a lot of time. It's on every operating system because these browsers are on every operating system, with the exception of iOS, because all browsers on iOS, the iPad, and the iPhone, have to use the same engine as Safari. It's available everywhere except for iOS right now because all the browsers on iOS are built on the Safari engine, really at their core, so we have to wait for Safari to finish supporting it. So, we've got crypto in the browser now through this API. Why do we need it? Isn't SSL TLS enough? Doesn't that provide security? It turns on a little lock icon. What else is necessary? There are some use cases where TLS does not solve the problem. And some people say that you can't really do anything secure in the browser anyway, but in fact, you can. The problems are that you're delivering code on demand to the browser, but nowadays most platforms have auto-updating. They have the same issues. You just have to be careful to make sure that the correct code is going into your browser. So here's the use case we have. You've got 2 users on laptops that want to talk to each other. They want to know that they're talking to each other, that the messages came from the correct person, and that nobody has been able to listen in. Well, normally they might talk to each other by each connecting to a web server that echoed their messages to back and forth, but HTTP is not even remotely secure. Anybody can listen to the connections. Anybody can alter those connections as well. So we use TLS, and the users get a nice lock, maybe even a green lock, indicating that your connection is secure. Well, your connection to the web browser is secure at that point, but not necessarily your connection to the other user you're talking to. That's because the server in the middle can see your messages and alter them. There are a lot of use cases where that's fine, where you can trust that server in the middle, but there are also use cases where you can't. In my company's case, we actually provide an internet solution for sealed bidding for highway construction projects. If a contractor wants to build a road, they have to submit a bid to the DOT, and they submit it to our website, but it has to remain sealed. our web server must not be able to read it. So we need to use end-to-end encryption. End-to-end cryptography lets the senders of a message sign and encrypt the messages in their browser before they ever leave their machine. Then they're passed through intermediate points on the network, on other servers, it doesn't matter, but none of those people can read or alter the message until it reaches the actual recipient, who has the ability to verify the signatures and decrypt the messages. So with the Web Cryptography API, we can implement that by having the code in the browser sign and encrypt the message before we send it out. It then passes through intermediaries like the web server, and the recipient can actually read the messages and tell who they're from. Of course, some people, when they heard that, went to the opposite extreme and said, well, okay, I see why we need web crypto, but then why do we need TLS? Well, in fact, if you don't have TLS, you have no idea what code is being delivered to the browser. So TLS protects the delivery from the server to the browser. You really have to have it, or there's no point in trying to do cryptography with code that you didn't necessarily write. Any questions on this background before we actually start talking about the API and how we're going to use it? Okay, yes?
So TLS, how does the man-in-the-middle attack actually work? Because doesn't TLS exchange keys and everything? Right?
TLS ensures that the connection you have between your PC and the web server is secure and cannot be eavesdropped on. But the web server is the man in the middle in this case. That actually is an endpoint, reads it, and then re-encrypts it in TLS to the next person. That's why we need to have end-to-end encryption for certain use cases. It's also useful for digital signatures so that you can actually have a document that you keep on file for a year and you can still prove it was sent by the correct person. You don't have to show, hey, I've got a live connection where I know who's at the other end of it. Yes?
So in this case, would you not use TLS and just use regular HTTP?
I'm sorry?
In this case, would you just use regular HTTP to send the packet because it's already encrypted?
Your messages can go over regular HTTP securely, but you're going to have to get your code into the browser using TLS in the first place. So I don't see any real reason that you wouldn't want to use TLS and web crypto both. You know, a belt and suspenders approach to this. Okay, let's talk about the API itself. The API lives in the browser's document object model. It's not part of the JavaScript language. So for example, it's not available in node.js unless you have a third-party module that implements it. It lives in the window.crypto object, and that object has one method called getRandomValues that takes a buffer, a chunk of memory, and fills it in with good cryptographically secure random numbers and returns it to you. That's not terribly exciting. All of the really exciting stuff lives in an object called window.crypto.subtle. That's where the methods are that we're really going to use today. So we're going to take a minute to actually go into the console. You're all welcome to do this. I'm going to show it on slides. So open your JavaScript console, Control-Shift-I for most browsers, F12 for Edge, and go to a secure website. And I recommend you just go to engelkey.com because that'll redirect you to a secure website. Once you do that and you're in the console, you can go ahead and try this getRandomValues method. The first line that you would type is something that creates a memory buffer. So buff equals new uint8 array parenthesis 16. That says I want to create a memory buffer that holds 16 unsigned 8-bit integers. That is to say, a memory buffer that holds 16 bytes.
Some people haven't gotten on the internet yet. That's the password.
Some people are still having trouble getting on the internet here. The password is fluentconf, all one word, all lowercase. Fluentconf. Okay, so you create this new array. It's not a JavaScript array. It's something called a typed array that's relatively new to JavaScript. Once you get that buffer, you can then pass it to window.crypto.getRandomValues. That is going to fill the buffer in with random data and return the random data, the buffer itself. So you can see the return value and you can see the buffer you passed have both been filled in. So I'm going to go through those step by step again. Buff equals new uint8 array, parenthesis 16. That allocates a memory buffer big enough to hold 16 sequential 8-bit integers. 16 bytes. That's a typed array. It's more like a C array in that these elements are contiguous and all the same, not like JavaScript normally is in arrays. And I'll usually call this a byte array, just because it's shorter than uint8 array. We then call window crypto get random values with that buffer. That takes an array buffer, which could be an array of 8-bit integers. There's also uint16 array for 16-bit integers and so forth. Any kind of typed array can be passed to it. It'll fill it with cryptographically strong random values and return that buffer to you. Now, this isn't really doing any secrets. It's not doing any secrets. It's not authenticating any code. So what's this got to do with cryptography? Well, to be secure, most cryptographic operations need good randomness injected into them at various places. So this is a starting point. You're going to see that we need to do this to do some of our operations. We're going to use this instead of a pseudo-random generator, for example, written in JavaScript, which is going to be too predictable. This random number generator goes to the native library. It can use system entropy. The one weakness of it is it's synchronous. You'll notice that we immediately got the answer back. We didn't have to give a callback. We didn't have to wait for the operation. That means that it's not necessarily going to be able to do the best possible randomness, waiting for your system to have more entropy. All right, that's a good dipping our toe in the water, but really all of the work comes in the subtle crypto API, living in window.crypto.subtle. This is called subtle crypto because, to quote the spec, many of these algorithms have subtle usage requirements in order to be secure. So you can use a really good, strong cryptographic algorithm and get properly encrypted output and still be completely insecure. Or maybe not completely insecure, but, well, actually, might as well be completely insecure. There's not really, I'm a little bit insecure. You're secure or you're not. So by calling it subtle, the API writers are putting users on notice to be careful, that they have to understand the requirements of what it takes to use the algorithms properly. All of the methods in subtle crypto are asynchronous. They all might take a long time to operate on. They all might have to wait for more entropy to operate. So they're asynchronous. You invoke them, and they come back to you right away, but they haven't necessarily finished the job. Traditionally, for me, I would expect when I invoke it to give it a callback and say, when you're ready, call this function. It'll handle the result. And in fact, that is how the spec was written in the early days before it was reached candidate recommendations level. But they decided instead to use promises, which turns out to make it much easier to write a lot of these operations. This is the first situation where I really used promises was with a crypto API, but it helps a lot. And if you're not too familiar with it, don't worry, we'll show you enough to operate with it. There are a dozen of these methods. We're going to do hands-on with 8 of those 12. So we're going to do cryptographic encryption. We're going to do digital signatures. We're going to manage the keys. So here's another hands-on example you can do with the console. And I'm going to go through these 2 lines of code one after another. The first line of code is going to generate a new key that we can use to encrypt and decrypt information. That will return a promise. We're then going to use the promises then method to tell the promise, once the promise is resolved, once the key has been generated, here's a function that will operate on the key, do what's necessary. So let's take a look at those lines one after another. To generate a key, now if you look up cryptographic keys, you're going to see that for some cryptographic algorithms, they're just bit strings. For other cryptographic algorithms, they might be large integers, that sort of thing. But the API doesn't work with any of that. The API requires you to encrypt using a crypto key object, a kind of object that only the API can create. So we're going to tell generate key, please create a random key usable for the AES-CBC algorithm. We're going to talk about what that means in a minute, of length 256. The second parameter, which is a Boolean, says whether we can export this to a bit string later or not. If we want to see the bits, we can export it. If we just want to use the key, we don't have to be able to export it. And then the third and final parameter is a regular array of strings saying what we want to do with this key once it exists. We're telling the API that we want to use this resulting key to encrypt and decrypt information. As I said, that returns a promise. So if you look at it in your console, let me go back a second, you'll see that the promise status was pending. If you go back after a few seconds and just say, show me what P is, you'll see that the status will have changed to resolved. Regardless of whether it's already resolved or not, we can then tell the promise what to do with the result when it finally exists by calling its then method and giving it a function that takes the result. And in this case, we're going to save the result in a global variable called key so we can look at it in the console later. And when we looked at it in the console, we saw that that key was a crypto key object. Now, for security, crypto key objects have a really nice feature. The actual value of the key is not exposed to the browser. Remember, the cryptographic operations are happening in the native libraries, they're not happening in JavaScript. So you're actually asking the native libraries to do stuff. They need to be able to see the actual key. The JavaScript code generally doesn't need to be able to see the key, so crypto key doesn't allow you to see it. That means that if somebody breaks into your machine and gets a hold of a crypto key, well, they can use it, which you probably don't want, but they can't steal it. They can't copy it out. That's both a plus and a minus because, of course, sometimes you've got to give keys to other people so you can communicate with them. But we work around that. There are ways to deal with all of that. The other thing is if you want to keep a crypto key object persistently, it's tricky. You can store data permanently inside the browser and come back in a few days and have it still be there if you go to the same website using local storage. Well, local storage will not store a crypto key. However, indexed DB, another mechanism for persistent storage, will store a crypto key. So you can persistently store a key that you can't see the value of, and it's a pretty safe way to do it. There is one thing on this console example that we did wrong, and that is we didn't deal with the fact that that operation might throw an exception. It might fail. And whenever you're dealing with promises, you should always make sure to include a handler for what happens if the operation fails. And the way to do that is with the catch method. You give it a function, it's given an error object, and you handle that error. Even if handling is just putting up an alert telling the user, we're not going to be able to do what you asked for, at least there's some acknowledgement that it didn't go right. Okay, some of the JavaScript you need in order to use this API. We've already mentioned array buffers. An array buffer is just a chunk of memory. You can't do anything directly with an array buffer. You need to actually have a particular typed kind of array buffer. So you can have an array buffer where you say treat it as if it is a sequence of 8-bit unsigned integers or a sequence of double length floats, whatever you want to do with it. I do have to warn you though, if you use anything but 8-bit integers, you run into a problem called endianness. In other words, if you've got a 16-bit integer that's 2 bytes long, is it stored in the order high order byte followed by low order byte, or is it low order byte followed by high order byte? For some reason I don't understand, the JavaScript spec decided it's going to be neutral on that. Every browser can do it differently. So it's not very useful in my mind to use anything but 8-bit arrays. And we've already seen the crypto key object, which is an opaque object created by the API. You can't manipulate the array buffer, but you can cast it. So here we have an example in the middle of this slide. A byte array is equal to a new uint8 array built around a buffer, an array buffer. It's the same object. If you change byte array, you're changing the original array buffer, but you can actually address each individual piece of it and change it. Promises, we've already mentioned. They are an object representing a deferred result. Promises have a then method where you give it handlers for success and failure, or you can give it just a success handler, and catch can be given just the failure handler. And the nice thing about promises that we are going to see, and is going to be clearer when you've done it a few times, is you can chain them. So if the result of calling the first method is a promise, you can invoke its then method with a handler for success. What is returned from that then method is another promise that has a then method, that's another promise that has a then method, and so on. And eventually you can end it with a .catch. If there's an error in any of these promises, those exceptions will fall through until the first time there's a catch. What's returned by the promise? Well, the then method is going to always return a new promise. What's that promise going to do? If the handler inside the then method returns a promise, the then method is going to return a promise that behaves the same way. But if the handler in there actually just is a regular thing, maybe it returns an integer, then the then method is actually going to construct a promise that will yield that integer to its handler when it happens. That sounds very abstract even to me right now. We're going to see it in use. Yes? I'm sorry?
You said inside of the event state you can have a prompt.
Yes.
And so what happens if
If you return a promise where you've already had a catch, if there's an exception, it'll be the catch, and the catch will return a promise that doesn't, I think, have anything in the resolution.
Correct, but what I'm saying is, in one of your then statements, you have a promise, you have a then inside of there, and you have a catch inside of that one, so then the catch will return it and just exit out and none of the other.
Yes, I think as soon as you hit the catch, you're not going to go on. But I'm not an expert in promises. I know enough to use them for the API, and that's about it. And I also know enough to know that they make my code a lot more legible. Maybe it makes me just think it's more legible, but a lot more legible than when I have callbacks. Now, it doesn't matter if there's one asynchronous operation. A callback's not a problem. The thing is, you're going to see a lot of these labs. We're going to do multiple asynchronous operations, one after another. And this way, it's a lot easier to make sure we finished one step before we started the next step when we use promises. Okay, any other questions before we get hands-on? All right, we're going to do 5 labs today. And I hope to get through the first 2 before the morning break, and then we'll do the remaining 3 afterwards. We may actually not completely finish the second one, but we should get far enough along that you'll have had a chance to get started on it before the break and then finish it right after the break. We're going to do symmetric encryption with a random key. And this is the one algorithm that we're also going to implement in Internet Explorer 11, just so you can see what's involved in supporting IE 11. Then we're going to do password-based key derivation for symmetric encryption, digital signatures, public key cryptography, and our last lab, we're going to create an X.509 self-signed certificate, the kind of certificate you might put in a developer's web server in order to be a secure server. Each lab is provided in a skeleton that is in the labs folder, number whatever, labs/1, labs/2, etc. And inside that folder, there are an HTML and CSS file that provide the page structure. There's util.js and wiring.js that have helper functions. Util has a lot of functions that convert between array buffers and strings, including hex-encoded strings and base64 encoded strings. Because inside our file system and inside our pages, we really need strings most of the time. But the API always wants to work with buffers. And then your solution goes in lab number whatever.js. There are working solutions available for all of these in the solutions folder. So, symmetric encryption.
Does anybody still need a copy of
All right. The basic concepts of symmetric encryption are that you're going to use one key, which is called the secret key, to encrypt and decrypt data. So if you've got that key, you can decrypt data, which is why it has to be a secret key. If everybody knew it, you wouldn't really be doing any good by encrypting your data. The original data is always called the plain text. The encrypted data is always called the ciphertext. The secret key has to be shared with all parties that are communicated, and that is the weakness of symmetric cryptography, those key exchanges. That really has been the main thing that probably has tripped up spies over the years, that they've had trouble exchanging keys and had to use them in insecure ways and allowed intelligence agencies to then decrypt their messages. To do this, you've got a symmetric algorithm. You take plain text, you take the secret key, and you get ciphertext. And the reason it's symmetric is you can go the other direction as well. You can take the ciphertext and the secret key and get the plain text back. There are 2 families of symmetric encryption algorithms called stream ciphers and block ciphers. Stream ciphers encrypt data essentially 1 bit or 1 byte at a time. So if you've got 73 bytes to encrypt, they'll encrypt those 73 bytes one after another. Block ciphers encrypt data in blocks. So for example, they might be blocks of 8 bytes at a time or 16 bytes at a time. You may have heard of things like one-time pads or RC4 or Salsa 20. Those are well-known stream ciphers. Block ciphers, everybody I think has heard of DES, the data encryption standard from the 70s that banks used for the longest time. IDEA is the block cipher that was used by the earliest good versions of PGP, pretty good privacy. And AES is the current advanced encryption standard. There's also a modern block cipher that people think a lot of called Blowfish. So the first thing you got to do is decide which of these to use. But the API has made your life easy. It only supports one of them, so your decision is going to be really, really simple. And we're going to see this over and over again in this API. The cryptographers that were involved in developing the API decided that they did not want to create a toolkit that could do anything, because that would take the normal developer and just present them with choices that they didn't know enough to make a good decision on. Instead, they were going to say, we're going to give you a toolkit that can meet your use cases, not necessarily do every cipher. You need to do symmetric encryption, we're going to give you one way to do symmetric encryption using the advanced encryption standard. Now, with block ciphers, they only encrypt fixed size blocks of data, so you have some issues. Some people will take the data, they'll add some zeros to the end to make it a multiple 16 bytes long, and then they'll just encrypt each block with the same key. That turns out to be very insecure because lots of messages tend to have repeated data, and if you encrypt each block with the same key, your output's going to have repeated data, which is going to give away part of your information. So cipher modes are how we deal with these two issues, how we pad that last block to get a multiple of 16 bytes, and how we encrypt each block in a unique way so that if we have repeated data, we don't get repeated ciphertext. Here's an example of why those modes matter. This is a well-known one. We have a picture of the Linux Penguin tux, and if you encrypt each block of that picture with the same AES key, you get the output shown on the right, which is encrypted. It's really, really well scrambled, but you can get some idea of what the message is about by looking at it. There are 5 different modes that the API currently supports. The one we're going to use today is cipher block chaining, or chain block cipher. I never can remember the order of the C's, for AES CBC. It's very widely used. So far as I know, every library that supports AES at all will support this mode. It does have one weakness in that somebody can mess with the ciphertext and you won't necessarily know it. You may get gibberish when you decrypt it, but you won't know why. Maybe the guy originally encrypted gibberish. But because it's so widely supported and it's in all the browsers, this is the one we're going to use. It's a good choice, just not the very best. The general feeling seems to be that the best choice is a mode called GCM for Galois counter mode. That's not in Firefox for Linux yet, for example. It's not in all browsers, even for TLS, even though it's considered the better mode. It probably will be in a year or two, so keep it in your toolkit and be prepared to switch to it then. There are also modes called counter mode and cipher feedback mode that are out there. And they probably are going to be dropped because we don't have 2 browsers implementing either of those modes. And there's not a lot of pressure to do that because the feeling is they don't add anything to the usability of the API. There's no reason you would want to use one of those modes instead of CBC or GCM. Or the other reason might be you're dealing with somebody who's already encrypted something with those modes, but that kind of interoperability was not a motivating factor. They said, let's let the web stuff be able to do it and make everybody else accommodate to them. There's a mode called AES Key Wrap, KW. It's a specialty mode just for keys. I've never used it. If I have to encrypt a key, I've just encrypted it like I'd encrypt any other plain text. But you can use it if you want. There are supposedly some advantages to it. As you can tell, I'm not a cryptographer. I'm a user of cryptography. So if we want to encrypt something with AES CBC, we start with the plain text and the key. You do that for encrypting anything. And then you need one more thing. And this is what stops a lot of people when they have to go use AES. The other thing is called an IV or initialization vector. This is 16 random bytes that is put at the beginning of your plain text for encryption so that if you encrypt the same text over and over again, you get different ciphertext each time because you've put different random data at the beginning. And you don't have it as a secret. You pass the initialization vector to whoever's going to decrypt it. They need to know it as well. But it does need to be different every time. So this is what we're going to use that get random values method for, to create this initialization vector. So decryption is just the opposite. The person who wants to decrypt the ciphertext needs to also have the initialization vector and the key. With that, they can just run the decrypt operation and get the plain text back. Now, to do this with the API, we've got to deal with the fact that the key is logically either 128 bits or 192 bits or 256 bits of data. But the API will not encrypt with a bunch of bits. It will only encrypt using a crypto key object. So the first thing we're going to have to do is get a crypto key object that we use. And there is a method called generate key that will do that. We want to be able to take the key to other browsers though, and crypto keys, there's no way to print it or type that in. So we will have to have the ability to take the crypto key object, render it onto something readable, take the readable thing and bring it back to a crypto key object. Those are the export key and import key methods. So we're going to see all of them in use in this first lab, all those three. And remember, all the data in the API needs to be in array buffers. The plain text, the initialization vector, the ciphertext, and the exported keys are all going to be array buffers. So if we want to display them in the browser, we're going to have to use those utility functions to convert them into strings, or hex-encoded strings if they're binary data, or base64 encoded strings. So here's a picture of the application for Lab 1. Let me bring up the live version of it. We have 3 buttons. One button will generate a random key, export it, and put the hex encoding of it here into our web page. So every time I click it, I get a different good random key. The encrypt button will take whatever I've typed into the plain text and it will create a random IV and use that to create ciphertext. So there we have the ciphertext. Now if I just get rid of that, the decrypt button will take the key and the IV and the ciphertext and get the original plain text back. You can take the exported key and the IV to another browser, a different kind of browser on a different operating system, plug them into the same web page and decrypt ciphertext. And you can do the opposite. If you encrypt something in a different browser, you can decrypt it here. That interoperability is really important. You don't even have to use a browser. You can use something like the OpenSSL command line tool if you want. So the skeleton is in lab/1. The non-crypto parts are already filled out. You'll fill in the missing parts of lab1.js. And for this lab only, we're going to actually do one of the 3 things you need to do together first. Then we'll take a break. You can all work on the other 2 parts independently. So we're going to do what happens when you click the button that says Generate Key. When the user clicks the button, we're going to need to create a random AES CBC key, and the specification is we want it to be a 256-bit key. By the way, any reason I would use 256 bits instead of 128 or 192?
You like bigger numbers?
That is the reason. You like bigger numbers. You're going to have customers, managers ask you what kind of encryption you're using. And if you say we're using 128-bit encryption, they're going to say, why aren't you using 256? It's better, it's bigger. And in fact, in a lot of cases, 256 isn't actually any more secure than 128, and it takes longer. But you don't want to have to explain it to everybody. So I always use 256-bit. That's all there is to it. It's fast enough. After we create the key, we're going to have to export it to an array buffer. And then we can take that array buffer, convert it into a hex-encoded string, and put that visibly into the form. So we start in the skeleton. If you look, the function for this is just called generate key. This is not the window crypto subtle generate key. It's just our application's generate key. Right now, when you click the encrypt button in the lab, you're just going to get an alert telling you click the button. So let's build on this one thing at a time. And please raise your hand and slow me down if I go too fast.
I have a question.
Yes?
Few slides back, in the theory section, you have a stream versus a block, right?
Yes.
What are the differences and why are we using block? And what's the main difference in the concept?
Okay, stream ciphers versus block ciphers. Well, to my mind, the easiest way to understand the difference is to realize that every stream cipher essentially exists as a pseudo-random number generator that creates a random stream of bits. And the way you encrypt is you just XOR your plain text bit by bit with the random series of bits coming out from that random number generator. And the key for the stream cipher is the seed of your random number generator. So that's logically how they work. They're very simple to understand. But if you end up reusing the same key in a stream cipher, and you have 2 messages, you actually can get the original key back by just combining the 2 messages and XORing them together. There are secure ways to use stream ciphers. They're very fast, and one of the biggest advantages of them is you do not have to take the whole message, put it in memory. You can just take byte at a time, read it, encrypt it as you go. But block ciphers can take that block, that 16-bit block, and do a lot more to it than just XOR it with something else. They can shuffle the order of stuff, they can scramble it in a variety of different ways, and that is what DES, IDEA, AES all do. They mess the blocks up that way. So it seems to me they're generally going to be a little bit better. The disadvantage of them is they're going to be slower, they're going to be a little harder to build. You've got to deal with the fact that your data may not be a whole number of blocks. If you're certainly trying to encrypt a message as it goes live, you have a problem that you're going to have to wait for more data to fill a block up. But block ciphers are what we have in the API. So really, that's the reason we're using a block cipher here. I'd like to say it's good cryptographic reasons on our part, but it's our only choice if we're using this API.
So to help me clear up the mysterious initialization vector, with a block cipher, it is a chain. So in my mind, I'm thinking it's the output of that first block is actually taken into consideration on the next block.
That's correct.
So that initialization vector is giving me a different input to the next block, and that's why it's needed?
That's right. What the cipher modes all do when you've got a bunch of blocks is they encrypt them one block at a time, and the result of encrypting block number 10, for example, is used to involve encrypting block number 11. Which means you can't just encrypt the tail end of the message, you've really got to go through it in order. But it does, that's why we have the initialization vector, so we have a random first block. So even if the rest of the blocks are the same, because we're fixing in the output of the previous one, they all get encrypted differently.
What happens if you don't give any vector? Can you do that?
I'm sorry?
The initialization vector, can you just...
It's fairly common, particularly with libraries like OpenSSL, where they don't explain what the purpose of this is, and they'll let you just leave out an initialization vector, and they'll just use by default all zeros, for example, and you'll not know that you're really being insecure. That's one of the big things that the Web Crypto API people wanted to avoid, was people having it real easy to use one of these algorithms in an insecure way. But it's very common. People often do that. They use these algorithms, they don't provide an initialization vector, they're not as secure as they'd otherwise be.
Right, but I can see that you can give out a key, but then if you have to give an ID for every message you send, then I don't see how that can be. I mean, you can share keys for some time, and you can change it back and forth, but for every message, if ID has to be different, then I don't know how you can.
That's a very good point. The point is, if you've got two people who want to communicate, they've shared a key. But now every time one of them encrypts a message, the other guy's got to know the IV he used, and it's different every time. Well, the solution is the message you pass has got the IV and the ciphertext both. And in fact, most of the algorithms will package them together in one file. The first 16 bits of the encrypted file will be the IV, and everything after 16 bytes will be the IV. Everything after byte number 16 will be the encrypted data. So without you realizing it, you're actually passing two pieces of information in your encrypted message, the initialization vector and the ciphertext itself. In order to keep things simple on this first example, we're putting them separate. So if you wanted to use this first example, when you gave somebody a message, you'd have to say, here's the ciphertext and here's the IV you need every time you do a message.
But in the second example, we'll fix that.
Yes. The second example is also going to do symmetric encryption, and we're going to build on the first one, and we're going to do that packaging ourselves, so we only have to give somebody one file. Okay, so here's the skeleton. First thing I did was replace it with comments on the 4 steps I have to perform. Generate a key, export it, hex encode that exported buffer, and put that hex encoded string into the proper form element. So to generate a key, seems obvious, I'm going to want to use the subtle crypto generate key method. We actually saw this in the console a couple of minutes ago. We need to give it 3 parameters, the specification of the algorithm we want, and some of these specifications are on the back of the cheat sheet file that is in the repo. For AES CBC, you have to give it that name. That's the official name as far as the crypto API is concerned, and you need to give it the bit length, in this case 256 bits. Then whether we want to have the key be exportable or not. To use the key, we don't have to be extractable. But if we want to actually be able to hex encode the key so somebody can see it, we're going to have to be able to extract it out of the crypto key object. And then an array on what we want to use this key for with the API, we want to use it to encrypt and decrypt. That doesn't change the actual bytes or bits of what the key is, but it does change the crypto key object, and so the API knows what it's willing to do with this. This immediately returns before it's finished, because what it returns is a promise. And that promise says, well, if you give me a function as a parameter to my then method, when I know the answer, I'll invoke that function. So we'll do that. We'll have the then method, and we'll give it an anonymous function. When that anonymous function is actually invoked, it's going to be passed the result of generate key, which is the crypto key object. What are we going to do with that crypto key object? Well, our job at this point, we're not encrypting or decrypting. Our job at this point is solely to get this into the form so that people can see it and give it to other people. So we're going to export the key. So the function handler is going to call window crypto subtle export key. We have to tell it the format of the key, and for secret keys, that format is just the string raw, and we need to give it the crypto key to export. Now, in this case, notice I am returning the promise that export key returns to me. I had two choices here. Instead of returning the promise, I could have handled the promise inside the body of this anonymous function. But if I did that and had multiple promises, I would end up nesting. I'd have a promise nested inside the handler of another promise, nested inside the handler of another promise, and so forth. If I actually have my handler return a promise itself, that is the value that's returned by the then method. So the return value of my anonymous function in there, that promise from export key, is the return value of the then method. So that itself returns a promise that we can give a then method with an anonymous function that will handle the result of the export key. The export key gives us an array buffer, so that handler is a function that takes the array buffer. I don't want to go too fast here because this is a little tricky at this point. This is our second asynchronous operation. Okay, what do we do with that buffer? Well, that turns out to be the easy part. We cast it to a byte array so that the individual bytes can be manipulated. We find the field in the form we want to put it in, and then we put in the hex string version of that byte array. We use a helper function to convert the byte array to a hex string. Now, at this point, we're done if nothing goes wrong. We're writing computer programs, so stuff is going to go wrong, so we'd better put in a catch at the end of this list that will be given an error object if something goes wrong. And all we're going to do to handle that error object is pop up an alert and tell the user what that error message was. Any questions? Yes? To here? Okay. By the way, the solution I'm showing you here is in the solutions folder, if you want to go take a look at it there too. It's also, the slides are also in that repo folder. I'm sorry? Yes.
Yeah, his point is that if it doesn't work and you're not sure why, you look at our solution. And as a teacher, this drives me crazy, but yeah, it's right, because you're here to learn something, you're not here to get the grade.
Okay, I'm going to talk about what the other two algorithms are supposed to do, then we're going to take a break for about 10 or 15 minutes, and we'll come around and help you while you're working on it. So, in order to finish the lab, you've got to handle what happens when you click the encrypt button and handle what happens when you click the decrypt button. So for encrypt, when you click the encrypt button, you're going to want to read the hex encoding of the key that's in the form element. You're going to want to read the plain text from the form. You're going to get that hex encoded key and somehow get it into a crypto key object by first converting it to an array buffer and then using import key to create a crypto key. You're going to create a random initialization vector and save that in the form so it can be seen later. And then you're finally going to be able to encrypt your plain text with the key and initialization vector, base64 encode the result of that, and put it in the form. Decrypting basically is the exact opposite steps. The main difference is when you're decrypting, you're not going to create a random initialization vector. You're going to take the initialization vector you're given and use it, whatever was created when you encrypted. So let's take 10 minutes or so, I'll wander around, as will Lori, give you a hand, and when we come back, we'll review the overall solution. How many people got the encryption part finished? A few people who are not too sure. Don't feel bad. This is very quick. We're trying to let you get your hands a little bit dirty, but we don't have time for you to go and debug everything. Let's go ahead and take a look at the solution for lab 1. We've already seen what happens with generate key, so let's scroll down to what happens when you do the encrypt button. To encrypt, we're going to need to use the bytes for the key and the bytes for the plain text. So the first part of the solution is just pulling those things out of the form element and putting both those things into buffers, array buffers. So we get the field containing the key, we get the value, which is a string, a hex encoding, and we use the hex string to byte array helper to convert that to a buffer. We get the element holding the plain text, get its value as a string, and use string to byte array to convert that into a buffer. First thing, we can't do any encryption without a key, so we're going to have to import that key. We exported it in raw format. They're the buffer with the bytes. And the other 3 parameters are the same as we use for generate key. We need to give it the algorithm we want to use in length, whether we need to export this or not. And really, why would we need to export it? We're importing it. We've already got an exported version of it around if we ever want it later. And what we want to do with it? Well, we're only going to use this key for encryption. We could say we want to encrypt and decrypt, but we're going to throw this key away after we're done encrypting. We're going to have to build a new one for decrypting later. That returns a promise. So in the promise, we finally have our key. We create a random initialization vector with window crypto get random values. We want to put that in the form so people can see it later. So we get the form element, hex encode our string, our buffer into a hex string, and put that in the form. And now we're ready to do the whole point of this operation, which is to encrypt the data. It's almost a letdown. The algorithm specifier includes a property that has the IV in it. You give it the key and the plain text bytes. And the result in the then handler is the ciphertext buffer. So we take the ciphertext buffer, cast it to a byte array, convert that to base 64 string so we can put it in the element where it's visible. And at the end of the line, have a catch that shows an error if something went wrong. Now there's a lot that can go wrong. We didn't try to make this foolproof. The user can, for example, say, I want to encrypt before they put in a key. Or since what's in the field for the key is just a bunch of hex bytes, it could be not valid hex encoding. It could be the wrong length to be a proper key. A lot of things can go wrong.
I'm just curious. When you generate a key, you're supplying the string to encrypt and decrypt. Does that have any functional effect on the key you get back? Or is that
No,
sort of
that's a good question. We're going to see that again and again. Encrypt and decrypt are just things that the API stores so it knows what you said you wanted to restrict the key to be used for. But you could take a key that you created only for encrypting, export it to a bunch of bytes, and re-import it and say, I want to use that only for decrypting. It doesn't affect the actual logical value of the key, just the value that the API stores. Okay, decrypt is somewhat similar, but we're not going to generate a random IV. We're going to pull it out of the form. So instead of pulling just the bytes for the key and the ciphertext out of the form, we're also going to pull the bytes for the IV out of the form. Once we get those 3 things, we're going to import the key exactly like we did before, but when we're done importing the key, we want to use this to decrypt, so that's the usage we put down. Once we have the key, we return the result of the decrypt operation. We have to give it the crypto key and the initialization vector, as well as the ciphertext. That gives us the plain text, which we're going to put in a buffer, convert it to a string, and put it in the right element in the field. And again, catch errors. This is a pattern we're going to see again and again in the labs today.
I have a question. Say for this exercise, we want to see the key, right? That's for the exercise to say. Now, say you don't have to see it in real application. Then what will be taken out in the Yeah, like I said, import, export, or what if the,
Well, suppose you wanted to encrypt something that later in the same program you wanted to decrypt. So you just keep the crypto key object around. You never need to export it. You never need to see the bytes. You already have a crypto key. That's all that's needed for encrypting and decrypting. The reason you need to export it is if you need to take it out of this program and put it somewhere else. Because you can't take a crypto key object out of this program. You can only take a string out of this program. So you need to export it so you can see it as a string. So if you were sending me a message and you created a key, you would have to export it so that you could give me the key so I could later decrypt the message. Yes, there are cases where you do not need to export. Oops, sorry about that. This somehow moved. There, that's better. Now, one nice thing is if the key's not exportable, it's more secret. It can't be stolen. But it also can't be backed up. So there are cases where you want it one way, cases where you want it the other.
so we need the key for authentic, we actually need the hex.
We'll actually need the hex value of the key for a lot of real-world applications. Two different people communicating, all they can pass back and forth is, for example, the bit string or the hex encoding. They can't pass the actual internal crypto key object back and forth.
Are you able to specify your provider at all, or are you stuck with the Windows, underlying Windows API?
You are not able to specify what cryptographic library Web Crypto API uses. That's something that the browser vendor decided for you. So for example, Edge and Chrome on Windows use the Windows cryptographic provider. Firefox uses its own called NSS. On Linux, Chrome uses a version of OpenSSL that they've stripped down to be simpler that they call boring SSL. It's boring because it doesn't do as much, so it doesn't have as many vulnerabilities. But we have no control over that.